How do we actually draw them up, right? So we're looking at how do we draw these orbitals in a way that it makes sense. And last day we went through at the energy level. And so this is an energy level diagram. Where did I have that? Right here. This is that energy level diagram that we had drawn up prior, and the fact that 1s has the lowest energy, then 2s, then 2p, then 3s, then 3p, and then we jumped into 4s before we drew into 3d, right? So the energy level goes up like that. And this actually fills in the periodic table. 1s, that's hydrogen and helium. 2s, that's lithium and beryllium. 2p, boron to neon. 3s, sodium and magnesium. 3p, aluminum all the way to argon. And then 4s is your potassium and your calcium. And then we jump down to the 3ds. That's your first transition metals, right? From scantinadium all the way to zinc. Okay? So we fill out these energy level diagrams. Now, that's great. And that brings us back to this energy level diagram that we have here. And so I left you some time to fill this out last day. Okay? Most of you have this done up. Now, this goes all the way to, what? 7s, 7p, 6d, 5, so all the way to 7p. So if we go to our periodic table and we count down 7 rows, hydrogen, lithium, sodium, potassium, rubidium, cesium, friends, that completes the whole periodic table here. Basically, they're all here. Will I ask you to fill out an energy level diagram all the way to the 7th row? Probably not. Where can I see us stopping? Probably the 5th row, somewhere in here. Because remember, I wanted you to know about the S's and P's, what they actually looked like. Then the D's, I need you to be able to fill in, but we weren't even talking about the F's. Okay? So if we look at our energy level diagram, even though it carries on above that, and these F's are your lanthanoid and actinoid series, I want you to be able to fill out an energy level diagram as we go through this. So when you fill out an energy level diagram, I can't imagine you wanting to draw out exactly like this. Okay? But I need you to realize what energy is the lowest to the greatest. Okay? So I use my periodic table when I'm making my energy level diagrams. Okay, so I pull out my periodic table. Because remember when we used our periodic table, sorry, it looks something like this. It's not the greatest. But over here, this is your S's. Then there's your D's, and then there's your P's. It's not even to scale. But as long as you follow along your periodic table, you're going to be able to follow. The only thing is hydrogen and helium, they're on the outside because that's where their electron configuration makes them be, right? Helium is full valence shells at 2 valence electrons. So really helium, though, is over here. It's the second electron in that s orbital, okay? So the first row just has s's, so we write 1s. The second row on our periodic table has s's and p's, so we write 2s, 2p. Then we write 3s, and then 3p. We know there's a d, but they don't appear right away. The 4 s's appear, and then the 3 d's, and then the 4 p's. Now this is kind of a tricky diagram, okay? I get it, it's slightly tricky. We can write it a couple different ways, okay? So the big thing is energy level goes up, increasing. So you have to figure out, or you have to write them from low energy to high energy up top. So low energy is 1s. Then my next energy level is 2s. Then 2p. Now, what are the lines or the circles representing, or the squares? How many orbitals there are. So in s's, there are 1 orbital, 2 electrons. In p's, do you remember how many orbitals are in p's? 3. P's have 3 orbitals. They have px, py, and pz. Right? So whenever we have a p, we draw 1, 2, 3 lines. If you didn't want to remember that, what's another way we could remember? In that last bit of the periodic table, that very end over here, right? There are 6 columns. Those 6 columns represent an electron each. And remember, an orbital can hold 2 electrons, right? So how many orbitals do you need to hold 6 electrons? 3 of them, right? Just like over here in the s's, we have 2 columns, which means you have 2 electrons to fill in. So, how many electrons in an orbital? 2. So if you have 2 electrons, how many orbitals do you need? 1. Half the amount. So 1s, 2s, 2p. What comes next? We're at neon. 3 s's. How many lines or circles or squares do I need to draw? 1. What comes after 3s? 3p. How many lines do I need to draw? 1, 2, 3. What's after 3p? 4 s's. Okay? Because it goes from aluminum to argon, and then we come down to the 4th column. So we have the s's before we have the d's. Okay? So we have 4s. How many valence electrons are in s's? Or 2, but 1 orbital, right? Then comes those transition metals, which we've run into before. What do we have to remember about those transition metals? They're the d orbitals. Okay? How many columns are there in transition metal? 10. How many orbitals do we need then? 5. And the one thing to remember about those d orbitals is they're 1 less. So there are 3 d's, but there's 5 lines. Ooh, I hope you can draw 5 lines in there. 4, 5. After the 3 d's, what comes next? So after the transition metals, we run into the 6 columns at the end. And what are those? 4 p's. How many lines do we draw for 4 p's? 3, because there's 3 orbitals in the p's. If I carry on, what's the next thing I'm going to write down? The 5s. Okay, with the 5s, that's the rubidium and the strontium. And we'd write 5s with a single line. Then what would we draw? The next one is yttrium, right, the Y. Those are D's, because those are transition metals, so we'd write 4D, right, and then 5P. That's probably as high as I'll go. Some people are going, oh my goodness, I don't know if I can do this yet. And that's okay. With practice, it comes easy, okay, or better. I like the lines. Some other teachers or some other people like the squares, like was represented before in that diagram that I found off the internet. Other people prefer drawing, oh, there I am drawing a line already, circles. 1s, 2s, 2p, follow the periodic table. So 3 circles. So it would look exactly the same except for instead of drawing squares or lines, they draw circles. What's the difference between this one that I represented and the one that was just prior here? the fact that I didn't really judge the energy levels. I just put them one on top of each other, right? And so that was the least to the most. I'm going to expect you to kind of just do it this way, not to jumble it all up in that one, okay? That one was a better representation of the exact amount of energy that is found in each one of those orbitals, okay? So, how do we fill these out? Some tools to use it. The energy of the electrons increases as we move or add electrons, as we move up the chart. And the energy level, what n is equal to, the sublevels, as well as the orbitals. When we fill in these energy level diagrams, we start from the bottom up. We assume that energy in that atom or in that item is at the lowest energy level, because most often they are, unless they become excited and then they release some energy and fall back to ground state, is what they call. So we're going to always kind of draw our atoms at ground state, so what they would be if they weren't excited. When you're filling out electrons in your shells or in your sublevels, we fill horizontally across. So if we have like the 2p's, we have 2px, 2py, 2pz, we have to fill one electron in each level before we go crowding that thing, okay? So if we're filling out one, basically we draw electrons as arrows. So some people draw it like that, some people draw it as a full arrow or a half arrow. I draw it as a half arrow because when I go to fill in my 2 electrons, I have an arrow up and I have an arrow down, and that's 2 electrons, okay? Some people will fill it out like that. There's nothing wrong with it, okay? Either way you want to fill out your electrons. Good? Now, how to fill the chart. You fill orbitals with the lowest energy, the ground state, and move up. You can only have 2 electrons per orbital, or per line, or per circle. And when you're filling electrons, you fill orbitals of the same energy level, so you fill horizontally across. So you put 1 in px, 1 in py, 1 in pz, and then you come put the second one in px. Okay? Orbitals can have a max of 2 electrons. We're going to look at how can we write these electron configurations, and I'm going to show you multiple different ways. I just need to do some erasing. So let's do the orbital notation of nickel, first and foremost. Okay? So the first thing you're going to do is you're going to locate nickel on your periodic table. Where's nickel located on our periodic table? It's in the 4th row in the transition metals, right? So what level is that? Is that 4s? Is that 4p? Is that 3d? Where's nickel located? What would you call that? Is that in the s's, the d's, or the p's? It's in the d's, okay? And if it's in the 4th row in the d's, it's actually called 3d. So the first thing you need to do is when you're given an element, you got to figure out how far do I have to go up? Because I'm going to guess you're not going to want to draw all the way to column 7 or 7s and 7p if you don't have to, right? You want to do the least amount of work, just like electrons wanting to be at the lowest energy level, ground state. Okay? So we have to go to 3Ds. So some people will count the lines, 1s, 2s, 2p, 3s, 3p, 4s, 3d. That's 7, okay? Because we have to start at 1s at the very bottom. It depends on how much room you want to leave between. So I would go 7 lines down, and I would write 1s. Then I'd write 2s, 2p, but draw 3, 3s, single line, 3p, 3 lines. What comes after 3p? 4s, how many lines? And then, what's after 4s? 3d. And how many lines for d? 1, 2, 3, 4, 5. Okay? So I decided how many orbitals I needed to draw by locating it on the periodic table, figuring out what it was, and then I counted up to see how many lines down I had to start. Or some people are really good at counting backwards. They would go 3D, 4S, 3P, 3S, 2P, 2S, 1S. And they could write it backwards. That's perfectly fine if you can do that. Okay? Question?
Does it matter which side the line's on?
It doesn't matter which side the line's on. Some people write the 1S's all on the left-hand side and then draw the orbitals the other way. That's perfectly fine. I always do it this way because this is the way that I was originally taught. I don't think it really matters either way. So, how many electrons, now this is going back old school, grade 10, grade 9, how do we figure out how many electrons are in a neutral atom of nickel? Number of electrons. If it's neutral, that's equal to the number of protons, right? How do we figure out the number of protons in nickel? The atomic number. So what's the atomic number of nickel? I can't read it. 28. So nickel has atomic number 28. So that means it has the number of protons of 28. And because we're saying it's neutral, or it's just a regular atom, it's going to be 28 electrons as well. Okay? If it had a charge, we'd have to change those depending on what ion it was, right? If it was nickel plus 2, what would happen, you guys? You would have 2 less electrons because you wanted a positive 2 charge. Okay? But here it just said neutral nickel, 28, and then we just have to count as if we were in grade 1 or in kindergarten counting to 28. But we just have to remember, as we fill the orbitals, we go 1 electron in each orbital for each horizontal line, and then draw the second one, and then go up to the next horizontal line. So it's like this. 1s, up, down, that's 2. 2s, up, down, that's 3, 4. And then 2 p's, 5, 6, 7. Notice I filled a cross, and then I'll fill 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. Now I have 3 more left. Does it really matter which orbital they belong to? They're all the same energy level. Okay? So as long as I have 3 more electrons in any of those orbitals, okay, as long as I have a max of 2 per. So I can go 26, 27, 28. But realistically, I don't know if I can move them. They could have been over here in this orbital or over here in this orbital. Where am I going? Sorry, my board isn't quite calibrated and it's freaking out on us. Is this okay? Luke?
So it doesn't matter where you put yourselves?
Like these 3 could be over here, right? in the next orbitals, as long as you filled up one per orbital, then you can go back and put the second one through. Okay? Now, this is called orbital notation. I am not a great fan of orbital notation because it's long. Okay? I like things to be short and concise. This is really nice, we can view it. But I like something called electron configuration. Okay? So the electron configuration goes as such. 1s squared, 2s squared, 2p6, 3s squared, 3p6, 4s squared, 3d8. This is number 2. This is the electron configuration for nickel. Do I need to explain how I got those numbers or what those numbers represent? Okay. So 1s is the sublevel and their principal quantum number, right? 1s. What does the 2 represent? How many electrons are in that orbital? Okay? So 1s squared, 2s squared really means in the principal quantum level 2 and sublevel s, there's 2 electrons filling there. 2p6 says in principal quantum level 2, sublevel p, there are 6 electrons sitting there. Okay? Now, sometimes this is short and concise. Sometimes scientists write it like this. 1s squared, 2s squared, 2px squared, 2py squared, 2pz squared. And I'm just going to go dot, dot, dot. Okay? That is still electron configuration. And it's still a proper electron configuration if I carried on. Why? Because it's specifically talking about the sublevel P in the x direction, in the y direction, and in the z direction. Okay? So with that being said, it's just a more exact placement. Okay? Same thing. You can write it like the original one, where the p's aren't separated out, but you should be able to read both. Okay? You could write both if you really wanted to, but I definitely need you to be able to write the first way. Is that okay? But you should be able to read both ways. Is this okay? Do you want to try another element? I want you guys to try, just on your own right now, can you try, let's do sulfur. Can you write both the orbital notation, the first kind, and the electron configuration of sulfur? So for sulfur, where is it located? What row and what sublevel? Sublevel P, quantum principal level 3, right? Third row. So we have to draw to 3p. So 1s, 2s, 2p, 3s, 3p. We need 5. Okay, so if I want to count down, I would leave 5 lines. This is orbital notation. Okay? Now, sometimes I'll ask you for orbital notation, sometimes I'll ask you for electron configuration. So you need to know the difference between them. Okay? So I would write 1s, 2s, 2p, 3s, 3p. Where there's s's, I draw single lines. Where there's p's, I draw 3 lines. How do I decide how many electrons I draw? Atomic number, that gives us the number of protons, right? So sulfur has 16 protons. Now, if sulfur, and I just said sulfur atom, it has the same amount of electrons, right? What if I said sulfur minus 2 ion? So how many electrons would I draw if it was a minus 2 ion? 18, because I need 2 more negative charges. Good, but because we didn't say that, we're left with 16 electrons because we said a neutral kind of atom. So basically, you guys would have drawn out something One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And now, no matter where I put that 16th one, I can put it right in the middle. That's full marks. I can put it out here, over here. Or I can put it really close right here, as long as I only put one in there to give me 16 full electrons. Okay? Because each one of those sublevels, Px, Py, Pz, are on the same energy level. So I can put that extra electron in either X, Y, or Z. Okay? So this is orbital notation. So how did we write our electron configuration? Can we talk to Jalen? Do you have your electron configuration? Okay. Who actually got that far? Go ahead, Kelly. 1s squared, 2s squared, 2p6, 3s squared, 3p4. Do you guys agree with her? Beautiful. Well done. Okay? That is your electron configuration. You should be able to do both. Are we happy with this? Okay? Because there's only 4 electrons. If I asked you how many electrons are in this sulfur ion/atom, so you don't really know because you can't just look up. If I asked you how many electrons are in this sulfur ion/atom, how would you do it if you were just given this? Add up all the exponents. That tells you how many electrons are there. So 2 plus 2 is 4, plus 6 is 10, plus 2 is 12, and I needed to get to 16, so 4 is 16. So that's how you know how many electrons. You keep on subtracting them off of the total amount of electrons. So if you don't actually draw this thing, this orbital notation, you'll still be able to figure out the electron configuration just by subtracting off. So let's try doing bromine and just the electron configuration. Okay? So I'll give you a minute here to do bromine and the electron configuration. Bromine. So looking at bromine, how many protons are in bromine? There's 35 protons because of the fact that that's its atomic number. How many electrons in a regular atom of bromine then? 35 electrons, right? Because if it's a regular atom or a neutral atom, it would have the same amount of protons. Now, where's bromine located? What do you have to write up till? 4 p's. Okay? So I've got to count 1s2, 2s2, 3, no. What's after 2s2, you guys? 2p6, so that's 10. Then 3s2, that's 12. 3p6, that's 18. Then 4s squared, that's 20. 3d10, that's 30. 4p, 1, 5. How do I know that it's 5? 5 plus 10 is 15, plus 10 more is 25, plus 10 more is 35. So it adds to a total of 35 electrons. Okay? Is this okay? Yes, Aaron?
Orbital notation, do those little ticks have to go through the line, or is it okay if they're on top of it?
If they're on top of the line, that's fine for orbital notation. They can go through the line or on top of the line, or you might even have circles drawn, right? So, let's move on to a shortcut method, because I know you guys prefer shortcut methods. This shortcut method can be used for both orbital notation and electron configuration. Okay? So, shortcuts are used when you have full shells or full energy levels. Okay? So, basically, to the full row on the periodic table. Okay? So, when we look at this, when writing out electron configurations, orbital notations for elements with large numbers of electrons, we can use a shortcut. Okay? This shortcut is to look for the last noble gas. Where are the noble gases located on your periodic table? The far right side, so column 18. You can use that noble gas and then carry on. So if I use neon, what's my next energy level? 3, and so I would start neon, and then I would go 3s2, 3p6, right? So it's basically cutting off the 1s2, the 2s2, the 2p6. Instead of writing that, you're going to write the word neon. But you have to write it in a special way. You write it in square brackets, and you use the symbol neon, capital N, little e. Okay? If you're going to use argon, you're cutting off 1s2, 2s2, 2p6, 3s2, 3p6, and you're replacing it with argon in square brackets A, capital A, little r. Okay? And then you just either carry on with the orbital notation above it or the electron configuration beside it. So let's look at phosphorus. Where's phosphorus? It's in 3p's, right? So what's the noble gas prior to phosphorus? Neon, right? So if I'm going to do that, neon is going to be my one right before it. So this is where I'm cutting off, okay? How many electrons are in neon? Just a regular neon. So we're using 10 electrons in neon. How many electrons do we have left? Well, I guess we need to know how many electrons are in phosphorus in the normal. 15. So we're going to use 10 in neon, so we'll have 5 electrons left to write out. So I'm going to do you guys want me to do orbital notation first? Or do you want to do electron configuration first? Okay, so if we do electron configuration, we would write it neon, and then after neon we're in row 3, and that's the S's. So I'd write 3s2, and then we go into 3p's, but I need to use only 5 electrons now. So I have 3 electrons left. Okay. So instead of writing 1s squared, 2s squared, 2p6, 3s squared, 3p3, you can write it in this method. Okay? I'm going to ask that you be able to do shortcut and long. Because on exams I've been known to take this and say, you have to do one long method, the rest can be shortcuts. Okay? Luke? I chose neon because it was the noble gas just prior to phosphorus. You have to use the noble gas just prior to the atom. Okay? So anything in row 3, I'll use neon. Anything in row 4, I'm going to use argon. Okay? So the orbital notation would look exactly the same. Sorry, I need to roll down here. The orbital notation would look exactly the same, except for we'd start with neon in square brackets, and then you'd write 3s with a line, and 3p with 1, 2, 3 lines. We put 2 electrons in the s's, and then the 3 p's has to look like this because you have to put 1 in every single orbital before you put the second in a single orbital. Okay? So let's try another one of these guys. Let's try iron. Iron symbol is Fe.
For which one?
Let's do both. Let's do both orbital and electron configuration. Iron. I'll leave you a few minutes here to work on it, and then we'll come back. Okay, so a couple of the first things you did, you looked up what's the atomic number of iron. The atomic number is 26, right? So then you figured out we have 26 electrons we have to deal with. So look for the shortcut. You look for the noble gas that's just a little bit higher than iron. What did you decide it was? Argon. Okay. So what is argon? How many electrons are in argon? There's 18 electrons in argon. So how many do you have left? You have 8 electrons left to fill in. Which one did you guys do first? Electron configuration or orbital notation? Okay, so the electron configuration, we start with argon. So I'm going to just write EC so we know that's the electron configuration. We've got argon. What comes after argon? Argon's the end of the third row. So then the fourth row is 4s, 2. So now I only have 6 electrons left. What's after 4s? 3d. So we write 3d 6, because we can have up to 10 there, right? Because D's can hold 10 electrons. So then we're done. That's it. Right? If I scroll down, I can also do the orbital configuration, argon, and then 4s, that's 2 electrons, 3d, that gives me room for 10. 1, 2, 3, 4, 5. And I only need 8 electrons, so I have enough room when I go to 3ds. Filling them out, 1 up, 1 down, that's 2, 3, 4, 5, 6, 7. And then I just have to fill out. Lots of times I just come back and start again. Does it matter where that last electron got placed? As long as it's in one of these orbitals. Okay? Are we happy? I'm going to do one more thing today. And that's the next page. Okay? The bottom just has like a little summary to make sure you're happy. But orbital notation and electron configuration of ions. Okay? Now, I think most of you know what an ion actually is, but an ion is an atom that has positive or negative charge so that it's either lost or gained an electron. So an ion is an atom that has positive or negative charge, and so it has either lost or gained an electron. What do they want to be like? They want to be like the noble gases. So they'll either lose electrons, that's like column 1, 2, and 13, like to lose electrons. Column 14 sometimes loses electrons, sometimes gains electrons. But then 15, 16, 17 gain electrons to get their full valence shell. Their valence shells are their S's and their P's. Okay? So metals, we know, are the ones that like to lose electrons. Nonmetals, they're on the right side. They like to gain electrons. That's the columns I was talking about, metals, nonmetals. Okay? That's because elements like to have the same number of electrons or become isoelectronic. Iso means the same. Some of you remember that prefix from biology when we did isotonic solutions. Iso, same type. Okay? To the noble gases, they remain as the same element. That means we don't change their number of protons, but we just change their number of electrons so that they're happy with their full valence shell. Becoming isoelectronic with the noble gases is energetically favorable in elements. Make them more stable. Okay? So let's do the orbital notation for copper 2+ without a shortcut. Okay? So where's copper anyways?
29.
Atomic number 29. It's right in front of nickel. I wonder why I did copper. Because it's stuck in the D's. Copper 2+. Should we do it together? Okay. So where is copper? It's stuck in, what, the 3Ds? And we're doing orbital notation, so that means start at the bottom and fill up, right? So we have 1s, then we have 2s, then we have 2p, I need 3 lines, then I have 3s, 3p, 4s, and then 3ds. And you said that's pretty much it, right? But I need 1, 2, 3, 4, 5 lines. Copper has the number of protons and the atomic number of what? 29. 29 protons. So if it's copper 2+, how many protons does it, or how many electrons does it have? 27 electrons. Okay? So not always will it work out to a noble gas kind of configuration, especially those transition metals, but we know copper does sometimes form a 2+. So if we fill it out, we're just filling out 27 electrons. 1 up, 1 down. That's 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27. So basically, 3D is filled except for 3 electrons. Yeah?
Are we supposed to write like something underneath it, or those are just for the show?
That's just for shortcuts. If I wanted to do a shortcut in this guy, where's copper? In the 4th column.
Argon.
So the one below it is argon, right? So if I use argon takes all the way to 3p. So then I just have 4s and 3d, and then you would fill it out. Sorry, I need 2 more things there. I just ran out of room. Okay? And fill it out like that. Now, I'm going to leave it here. We're going to talk more about shortcuts because this is a special more about shortcuts, more about ions next day, and then we'll carry into Lewis diagrams. Okay?